Hey, welcome to the channel Deep Learning Explainer. Yeah, this channel basically is the way that I can share the thing I learned from reading research papers, especially in those deep learning papers, and I will explain that with those PowerPoint slides as much as I can, and hopefully you can save your time that you don't really spend as much time as I did to understand those papers. Okay, so my channel is called Deep Learning Explainer. If you like to receive more videos like this, more videos about deep learning paper explaining, please feel free to subscribe. And it's also take a lot of time to make this kind of videos. So if you subscribe and give me a thumbs up, it's actually a very big encouragement for me. So without further ado, let's dive in. So this is actually the paper that I read recently and also published just recently. I remember just a few days ago, and immediately when I saw it, I felt it has a potential to revolutionize the way people do drug discovery or like material design. And yeah, I kind of I'm very interested in these kind of things. They combine the technique that usually people use in natural language processing domain. Maybe you heard of the transformer, the kind of architecture, and you kind of leverage the architecture that already gain a huge success in NLP domain. They leverage those kind of things in chemical domain, and they also prove that it's very effective. So this paper is called molecule attention transformer. Basically, it's a spatial type of transformer. They modify a little bit of attention mechanisms in a normal transformer, so it works better. This paper is mainly from the authors in Poland, and also some author from the US. Okay, so let's see the overview of this paper. At first, I will introduce why people want to do molecule property prediction. Basically, this model is to perform molecule property prediction. And before that, I will introduce you why we want to do that, what's the benefits that we can get from it. And secondly, I will did a brief introduction on how people did this previously, what's the traditional approaches, and what's a machine learning way to solve this problem. And after that, I will be talking about the molecule attention transformer, which is the main part of this paper. It's very interesting to look at it. And after that, the authors didn't only publish the modified version of the transformer, they also used the pre-training technique to train a very good, robust transformer model for the molecule property prediction, and it's proven quite effective. And if you've heard of BERT is actually a language model, pre-trained language model, and it's kind of very effective to improve the downstream tasks performance, and that's why transformers got so much popular, it's mainly because of BERT. And they also want to do the same thing for this molecule attention transformer. So that's a very important part of this paper. And lastly, I will talk about their experiment results. Actually, the good thing of this paper is they don't only do like 2 or 3 or 10 times like a training of the model. They basically do a lot of statistic significant things. Basically, a lot of machine learning papers, they claim their model are better. It's not. They just do maybe few different way of initializing model. But sometimes, if you just random initialize your model, or you just lucky get some lucky initialization, so your models outperform the previous models, but doesn't mean your model architectures are actually better. But in this paper, they actually do this in very statistical way to prove their models are actually better than the previous models, and they kind of do this part very well. So why do we need to do molecule property prediction? There are main two use cases. The first one is we can do drug discovery, because 85% of drug candidates fail the clinical trials in the US. So there's a lot of them fail. And if we can really predict the molecule property better, predict like how toxic these drugs can potentially be, then this kind of stuff, then we will increase our success rate a lot and save a lot of money, and kind of shorten the development cycle of a drug, and they will benefit so many people on Earth. And secondly, we can also use this kind of a technique to do the better material design, because currently we don't really have the efficient way to discover new material, the kind of things. Or actually we are quite efficient, but we can be more efficient. So one really cool application is we can have better batteries, because so far we don't really have a good enough battery to do the electric airplane. Yeah, that's mainly because we don't have durable enough batteries for that. So we can do that. And what people you normally do for molecule property prediction is, because every kind of a molecule behavior can be predicted by quantum mechanics. And if we can have quantum mechanics, those kind of physics knowledge, we should be able to really predict any kind of property this given molecule will have. But the problem is quantum mechanics somehow will get too complex to be really calculated in those kind of multi-body systems. And there are also a lot of approximate way to still layers to be able to calculate those molecule property. But the problem is it still require tons of computational power. So using the physics knowledge is the most ideal way, but we just don't have the enough power to deal with that. And sometimes when you have more and more atoms in the molecule, the computation just grows exponentially. So that's the main reason this way it's not perfect. And because of that, a lot of people actually come up with a machine learning approaches. But the problem is, it's like we don't really have the large data for that. So lack of data set is really big problem for machine learning approach. And the third one is like hybrid. We can actually combine some physics knowledge to impose the strong prior to the machine learning model. So those models don't really need to learn from scratch. I think this is the preferred way so far, and it's also how this paper is going to approach. So we will find out later. And there are some deep learning approaches, and most of them actually are outperformed by traditional machine learning models. For example, support vector machine or random forest, those kind of stuff. I think the main reason is we just don't have enough data for deep learning model to thrive. And usually those deep learning model for this task, molecule property prediction, is very hard to train. There are a variety of reasons, but in conclusion, they are just very hard to train. And also they require a lot of hyperparameter tuning. Basically means you need to spend tons of computational power for that, just to train a model, right? And then the performance is not necessarily good. Okay, so in the early time, people actually handcrafted. Okay, so before that, I want to just introduce a little bit. Even we do the physics knowledge way to predict the molecule property, we still need to know the atom arrangement, because like carbon dioxide is a simple example. We need to know where the carbon is and where the oxygen atoms are. And we also need to know how far away are they from each other, and those are geometric relationships. We need to know all that so we can perform our quantum mechanic calculation, those kind of stuff. So that's why for the machine learning model, you also need to have that kind of information, basically to let the model understand a little bit about physics. So early times, people actually handcrafted a lot of different way to present those molecules. Actually, one molecule contains many different kind of atoms, right? So people use their own way to represent that, but that's very time consuming and they require a lot of domain expertise. It's not really scalable. But nowadays, people like to see those molecules as a graph. So they use graph convolutional neural networks to kind of solve this problem. And the good thing of graph convolutional neural network is the deeper you go, and the more the model can see the whole picture, right? It's just like convolutional neural network. You go deep, then your feature will become more abstract and the more broad. Okay, so one very popular ways nowadays is 3D graph CNN. Basically, it's the CNN they can understand the 3D relation in the real world, and basically, if you think twice, you will understand those molecules are actually in the 3D structures, right? So it's actually a very good way to use 3D graph CNN to kind of build a predictive models. Okay, so these, and I'm going to introduce a little bit like transformer way to do this, perform this task. So last year, 2019, their Karpov, they use a transformer architecture and to do the molecule property prediction. And how they do that, they basically list the compounds as a sentence, and then they use a smiles annotation. Basically, smiles is the way to annotate those chemical compounds. And if you do it properly, you actually can treat one smile annotations as a sentence, and those atoms are like the word in a sentence. So this is the earliest paper they use transformer to do this kind of stuff. But I believe there are some other people that use recurrent neural network to do the similar thing. That basically use a smile annotation, but they just use a different architecture of neural networks to perform the task. So this paper, they actually combine they don't use smile annotation, they just combine the list of atoms. But the problem is, if you just put a list of atoms as a compound, the model won't be able to understand the physical relation between each items. Basically, it won't know the geometric relation, like how far away those atoms are, and are they close to each other? I mean, are they neighbor to each other? Those kind of stuff. Those adjacency relation. So they use some other way to address this problem, which I think is very elegant. Okay, so what's new in this paper? Since there already some people did a transformer, right? So what's new in this paper? Basically, they use the more complex attention mechanism. They don't only use the original transformer one, they also put two other ways to make the attention mechanism more robust. And they also perform their model. They also pre-train their model basically on certain data set, and they found out it's very, very effective. And lastly, this paper did a very comprehensive experiment. So like I say, they use a very statistical ways to say their model is better, which is quite convincing. So I would like to introduce what's a typical attention in transformer. Basically, we call the attention mechanism in transformer self-attention. What does self-attention mean? Basically, it's like when we have an input as when we have a sentence as an input. So like this sentence, then what transformer do, what BERT language model do is basically to generate the representation for every single word, every token in this sentence. So the animal, the blah 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 blah. So every tokens here will have one representation. But how the BERT model or transformer model generates this representation? Basically, it's like you will, let's say, if this transformer model already generate the representation for these previous words, and you want to generate a representation for the word it, and how it will do is like you will look at the other tokens in a sentence and to see which tokens are more important for the word it, and because you already learned certain like relation between word and word, and you roughly know it actually is the pronoun which represent the animal, so it will pay more attention to the animal. So when it try to calculate the representation means like the contextual representation, basically to represent the meaning of it. But it can represent many different things in different contexts because it's the proper noun, right? It's a proper noun. It's not pronoun, sorry, it's a proper noun. So it depends on context, and in this context, it basically represents the animal. So, but the model knows it actually in this context represents the animal, so it will pay more attention to the animal. So the vector or the representation for this it will contain the more semantic meaning of animal-related things. So that's attention. There's a self-attention. You look at yourself. The input sentence, like every word in the input sentence, and to design which words you need to pay more attention to generate the representation for this given token. And also the attention here, usually in a transformer, you will have like more than one attention head. Usually it's like 12, 16 attention heads. And different attention heads will encode the different relation. For example, this is like encode a coreference relation between words, and there will be some attention heads encoded maybe like other semantic relation or syntactic relations among words. So there will be a lot of different kind of interword relationships being modeled by the attention mechanism here. And same goes to the molecule, chemical compounds. For example, maybe this is, you can see this is our input. In the NLP context, we will represent this kind of a molecule as a sentence. So maybe we'll give a list of items here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and definitely we will have the spatial way to represent one molecule for the input. So the input is a list of vectors, and every vector represents one kind of atom. And if you are the same atom, maybe carbon here, the oxygen here, and oxygen here, we have the same vector, because before the transformer or your input, we just be the fixed vector for a given type of atom. It's like when we feed the input to the transformer, there's actually the first word embedding layer, and then word embedding layer will generate the fixed presentation for every different word. What I mean actually is, if your word is called it, and no matter where you are in the context, and your representation will be the same, because it's word embedding. You only embedding the words individually. It doesn't consider the context. And this is the same before the transformer block. You will only have the representation for each atom here. And after that, the attention mechanism will decide when we want to generate a representation for this oxygen, which kind of atoms in this molecule we need to pay more attention to. And there will be a lot of different relationship. So for example, maybe in chemical, the carbon like bonding, something like that is like will be important. So they will try to look at if there's that kind of relationship arrangement here, and pay, if there is, they will pay more attention to that. And this is for first attention head, and the second attention head will embed the different chemical patterns. They might also think that's important. Okay, so it's roughly how it works. If you already understand transformer, you'll be understand this in no time. But if you don't understand the architecture of transformer, I would suggest you go back to the papers or a lot of blog articles explaining how the transformer works. Just Google it and you will find out. Okay, so this is a molecule self-attention. So basically, it has one self-attention layer. Basically, it's this. This is the original, this form, this original transformer attention. So basically, you will learn which kind of tokens or molecules are important, so pay attention to that. And additionally, this paper add other information. It's like the distance. So if the distance is like farther, this is a distance matrix. So basically, they will describe the distance between each different atoms in this molecule, and it will design, if this distance is far, then just don't pay much attention. You basically adjust your attention matrix here by your distance. And there's another factor here is adjacency matrix. What adjacency matrix is like it will describe if this molecule number 10 surrounding molecules is molecule number 9, and the molecule number is molecule number 9, then the adjacency matrix, the value of their adjacency matrix will be 1, and with the other items will be 0. So actually, I assume you already know adjacency matrix. If you don't know, look it up in Wikipedia, you will understand. It basically is the way to describe if these two atoms are like border each other or not. Are they neighbor or not? Yeah. So that's adjacency matrix, and basically describe the geometry relationship between each other. So if those atoms like this oxygen 10 and oxygen 20, their adjacency pair, the matrix value of between them is actually 0. So the model will know they actually are far away from each other. You don't need to pay too much attention to that. Additionally, model also know the distance between them, so that's very important because some adjacency matrix like atom number 7 will be close to, will be next to atom number 6 and number 8, but maybe their distance are different. Maybe number 7 is closer to number 6, so in that context, you will not know from this information from the adjacency matrix, but you will know from the distance matrix. So that's how it works. So this paper actually modified this. They add another two terms to the attention mechanism, and this first term is actually originally from the Vanilla transformer, and they use the lambda value to adjust the importance of each factor for deciding attention. So this is like this kind of stuff, and you will get your attention matrix. Basically, is the matrix to decide how important atom is for the atom you are for a given atom. Yeah. So basically, after the attention matrix, you will know, maybe we are going to calculate the representation of this contextual representation of this molecule HO, and by that we will calculate the attention matrix. Then we will know which atoms are more important according to this matrix. So that's it. And as for how we represent atom before we feed the input to the transformer, like I say, in the NLP world, we will have the word embedding for each given word, and it's not really contextual dependent. In this context, we will also have the fixed representation for each given atom, and there are around 150 something different kind of atoms in the world. So we also have they many of different vectors to represent that. And normally in the transformer, we don't really hard-code these vectors for words. We also let the neural network to pick up, and we usually have like I think it's around 500 something dimension to represent each word. To this like 500 dimensional vector for representation of the word embedding dimension. It could be 500, it could be 2000 something. It's actually a hyperparameter that you can tune. And so in this context, we don't let model to pick it up. We basically encode some our physical knowledge or some chemical knowledges that we already know. We don't want model to pick it up, because if model, it's not like model couldn't pick it up. Model can, but you will need a lot more data set, because in NLP we have much more data set than we have in the molecule domain. So how we do that, and basically it's like we have several different dimensions, and in this context, in this paper, they use 26 dimensional vectors to represent atoms. So the first the 0 to 11 dimension basically is like they use this kind of one-hot encoding. If this atom is B and C, or like this kind of one-hot encoding means like if you are, for example, if you are carbon, then your vector will be 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, right? So if you are sulfur, your vector will be 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. So it's a one-hot encoder. I believe you already know one-hot encoding, so this is you just use the one-hot encoding way to represent that. But you will probably ask, why don't we use one-hot encoding to represent all the atoms in our periodic table? I think is what you call that. We just need a 150 something dimension to, no, I think it's not 150, it's like 200 something, 200 dimensional to represent that. So I don't really understand why the paper just picked this chem 11 on these 12 particular atoms. I think it's for a reason, because in a chemical, certain atoms are more important, like carbon, oxygen, sulfur, these kind of things, and the other like metal atoms maybe are not that as important in this context, and we probably don't use that kind of stuff to materials or generate the drugs, right? So that's probably the reason they want to reduce the complexity of the models. But you can argue if model have those 100 encoded for every atom in the world, model should be able to pick up this, because it's not dimensional. It's not that high. It's just 200 something. So you could do that, and maybe it's actually a better way to represent. I don't know. Maybe those authors actually they did this experiment before. Yeah. So apart from that, they will also have the different dimension, and that's in charge of if there's heavy number of heavy neighbors. I think this is very important in the chemistry. If you have more heavy neighbors, then you will have different behavior, and then kind of encode this kind of information here. And the number of hydrogen atoms is also important. And I think they definitely encoded this kind of features by their domain knowledge. So we need to believe them, because I'm also now a chemistry person. I'm a physics. So I don't understand that much. I mean, I don't understand the reason behind this, but according to my high school chemistry, it makes sense. And the formal charge, and if this is the ring, if this what's that? The word? Basically, yeah, this kind of stuff. And yeah, this is a aromatic. I don't even understand that, but I believe that's an important feature. Oh, this is the whole picture of the molecule transformer. So basically, your input is this one, and you will have representation for a molecule vector for each vectors, and we will list those vectors as just in order. So just imagine every atom is a word, and a molecule is a sentence, right? So your embedding layer basically is here. That will give you embedding, and after that you will have the transformer. Basically, one transformer will consist of several different blocks, and one block consists of one attention and one feed-forward neural network. So if you don't know it yet, look it up. Look it up from Google. You will understand a lot more. And if you really want to read the original paper of transformer, there will be a paper called "Attention is All You Need." I believe it was by Google, and that's a very, very good. But I believe it's a good paper. Okay, so anyway, you will have 3 different kinds of attention mechanism, and you will combine them. Or one is a self-attention mechanism. Basically, it's the same as transformer. You just treat as the molecule as a pure sentence. It's just a pure text, and deciding which words you want to pay more attention in this context, like which atoms that you want to pay more attention. And the adjacency matrix basically is adjacency matrix will describe your neighbors. Are you neighbor each other? A distance will decide like how far away from each other, and if you're too far away, we probably don't want to pay too much attention to it. If you don't neighbor to each other, then we probably also don't want to pay too much attention to it. And this self-attention basically is learn. You can pay the atoms they're very far away and they're non-neighbor to you, whatever you want, as long as the model feels that's important. And definitely how model learn that, model learning from data. And after that, you have the layer norm and the global pooling, basically to generate the one fixed set embedding. And the embedding will, after that, you will fix the representation to your fully connected layer and to the property you want to predict. Maybe it's a binary, it's a conductor or not. Maybe it's some other features, like numerical features, can be either way, depending on what kind of feature you want, and you will change your fully connected layers a little bit. And this paper actually performed this model to, I think, 6 or 5 something different molecule property prediction tasks. And to be honest, I am not familiar with those tasks. And if you are interested, you can look it up in the paper. But generally, those tasks are the performance of this model on those different tasks are aggregated together, and so they can compare. So they also compare this model with the other model, like the SVN support vector machine random forest and some other models. This is like the graph convolutional neural network. And they found out if you don't only do the 150 hyperparameter combination search, basically you only search for 150 different combination of hyperparameter, which consider now a lot. And their model called MAT, molecule attention transformer, actually is outperform the rest of the model. The number is like the lower the better, so you can see their model is better, but you can see there the range is quite big. It can sometimes be very good depending on your initialization. Sometimes can be a bit bad. Yeah, depending on your initialization and your hyperparameters. So it's a little bit unstable, I would say, compared to other machine learning models. It's not really stable because like the other people's like the interval is just smaller, right? But if you do more hyperparameter tunings, basically you search 500 different combinations of hyperparameters, and you will find out the model is the more outperform the rest of model. So the average of their value is like 2.4, and the rest of model not even lower than 3. So it's kind of a very good model, and in general it's much more better than the rest of models. So that's their achievement. I believe it's a quite an achievement. And after that, because as you know, the transformer model, why is so popular? Because there are a lot of pre-trained language models. For example, BERT, GPT, XLNet, those kind of pre-trained language model. Basically, they perform a self-supervised learning on a lot of different corpus, different corpus like Wikipedia, Google Books, those kind of corpus, and they pre-train that. Basically, they mask certain tokens in the corpus, and they try to use the transformer to predict that. By doing that kind of a self-supervised learning, the model can pick up a lot of language knowledge from those data, and that's why it is so powerful, right? And they also want to do the same self-supervised learning. Basically, it's like pre-training for their model. So they find out how they do that is actually they find other. It's actually, I don't really think have the same meaning of BERT, but they basically find the other data sets and perform the molecule property prediction. Okay, no. They have the molecule here, and they try to predict the property of different atoms in this molecule. So they call this self-supervised learning. So it's actually quite similar to the self-supervised learning in NLP. So for example, maybe in this context, we will mask the property of this atom, and we want to predict that. And we also in the next training we mask this, and we want to predict this atom's property, this sort of thing. I think the paper actually didn't really detail how they do that, but generally I think you get a concept. If you don't understand what the self-supervised learning is, look it up, Google it, and you will know. And they found out, I think this is where it gets interesting, when they do the pre-training. The pre-trained model actually is like far more outperform the rest of pre-trained model, or Yeah, this is like the smile. Basically, they also use a transformer approach, but just they didn't modify the attention mechanism, and they also use the annotation smiles annotation. They don't just put a list of atoms. So it's a little bit spatial, like chemical annotation, and the performance is far worse than their model. And the rest of model like graph CNN is also so far away from their performance. And as you can see, if they do the pre-training, their performance is like further improved to 1.5 something. It's like far better than non-pre-trained model. So you can see how powerful it is. It's like damn powerful. They improve the results so much and outperform the other previous best models so much. So we can know this probably will revolutionize the molecule property prediction world, the chemistry world a lot. I believe so. So remember this day, I think it's February 2020. Probably in the next 12 months, you will see a lot more papers around this line of work being published. A lot of people will probably use this kind of pre-train model, or they will use a little bit modified way to pre-train it and perform on different kind of a molecule property prediction task, and they will have a lot of good result. So just wait. And this paper also do a little bit interesting thing. They want to understand what their molecule attention transformer are looking at in their attention mechanism. Basically, they try to manually input the molecule and to kind of decompose the model's attention weight on this molecule, so we can know what kind of things this model is looking at. This is actually a lot of people do for the attention mechanism, for understanding it. So the model attention has actually focused on only a few atoms. It also makes sense because that's the reason why we call it attention, right? You couldn't like always pay attention to every atom. That's equals to not paying attention. So the first layer, they basically pay attention on very, very simple chemical patterns, probably the ones that you learn from the high school. And the subsequent layers, the deeper layers, it is the more complex arrangement of atoms you look into. Yeah, that's very interesting. Yeah. So basically, model learns some chemical knowledge, general knowledge, and some of them are very similar to what we already know. Yeah. So this is how you pay attention. So every different color of this in this graph actually represent the different attention head. For example, the red color, they pay attention to the one kind of chemical patterns. The blue colors here, they pay attention to different kind of a chemical pattern. So that's just how it works. Yeah, pretty similar to what how we decompose the attention the model is paying for NLP task. Different attention heads will have looking for a different relation. For example, one maybe looking for co-reference relation, one looking for verb subject relation, one looking for plural or singular relation. If you are familiar with NLP, then you probably can relate to that a little bit. So this is how it works. Okay, so here comes to the conclusion of this model, the line of work. I think it's pretty cool. And they're saying atom distance is very important because actually in the end they did the ablation task model actually rely on the atom distances a lot. And if you remove that feature, your model's performance will just decrease very significantly. And the pre-training is a key to wider adaptation. Yeah, I believe so, because if you have a pre-trained model that other people don't really need to train it from scratch, and they can use their pre-trained model to perform some downstream tasks. That's extremely helpful. Just like we use a BERT as a pre-trained language model. And if we want to do, for example, some sentiment analysis, then we can just plug in a bird to generate a representation of the word, and or maybe we fine-tune the bird a little bit on our sentiment classification task, so we can have the very, very good performance with the limited data set. And that's what the chemistry domain they need, because they don't have the huge data set for a lot of different tasks. And it's also very exciting to see how the people applying this kind of work, and there will be more and more applications, I believe so. So yeah, that's all for today. It's very intriguing paper and inspiring. I think if you are thinking you probably will never do chemistry, maybe you're a computer vision person, you're an NLP person, you don't want to do this kind of stuff. But I would say, even you don't do chemistry, by looking at this paper, you can see how other people apply the tools, the algorithms in other domain to their domain. This kind of way to, I would say it's like innovation a little bit. Definitely you need to have a strong understanding of the other people, the work in other domain. Then you put some creation, innovation, then you can have a very good work. I think it's a very important skill to have nowadays. For example, there are a lot of neural network architecture. They first started inventing in the computer vision domain, and some smart guys, some smart researchers, they imported that kind of techniques to natural language processing domain. I think this is what we actually need. That's very important. It's like aggregation of knowledge, transformation of knowledge. So by looking at this paper, I think will inspire you a little bit in terms of that. So that's all for today. And if you really watch to this end, don't forget to give me a like if you like the video. And if you want to receive more videos like this, don't forget to subscribe. It's like I say, it's quite hard, and I spend quite a lot of time to prepare this video. And your likes and your subscriptions will be a very important encouragement for me, so that I have more motive, have more incentives to make my next video, right? Okay, so that's all for today. And if you have any thoughts, questions, feel free to leave in the comment section below. And other than that, I will see you next time. It's